I think, I don't know, you should tell me. So the first thing is to design the differential pair driver to get the maximum amplitude. Now this part is, it's not really dependent on whether you have equalization or not. Eventually you can only get so much amplitude from the differential pair given a power supply voltage, and this happens because of the limitations on the common mode voltage at the output. Okay. And the structure we have is AC coupled, so that does make a difference whether you have, AC coupled meaning the load is not in parallel with the collector drain load resistors, the load resistors on the other side. Okay, there is no DC flowing through the load. So this is the transmit side, this is the receive side. Okay. As you can see, in when the differential pair has zero differential input voltage, the difference between these two is zero and no current flows through the load. Okay. But when the output is switching, current does flow through the load. Basically, there is no common mode load current. Okay. So this is similar to the AC coupled case. The difference is that for signal there is no AC coupling for the differential signal, but for common mode there is AC coupling. This is another type of termination that you could use. Okay. Is this part clear, that the load does not influence the bias picture? Yes or no? Okay. What I meant is, let's look at the difference between this case and where you terminate this with a certain DC voltage. Is that visible? So in this case, let's say this is certain VDC and all these are R. Now I assume that the input differential voltage is 0. By symmetry I know that the output differential voltage is also 0. Okay. So I can just write a single set of equations for the common mode condition. Let's say the tail current is I0. The current flowing through here, current flowing through here is I0. Okay. I0 equals VDD minus V0. In this case, V0 refers to the common mode output voltage divided by R plus VDC minus the output common mode voltage divided by R. And you can solve this given I0, VDD, VDC and the R value. You can solve for the common mode voltage, and of course you can also solve it if this is like some R1 and this is R2. The load does not have to be equal to the terminating resistor. Okay. Whereas if I write analogous equations in this case, I know that these two voltages are going to be equal at VOCM. Okay. Now I can go through the analysis, but what is this voltage going to be? This voltage. So let's assume that it is something else. What happens then? If this is something different from the output common mode voltage, there will be a current flowing this way and there is a current flowing this way. Okay, but you can't have DC flowing through the capacitor. So if that does happen, then the capacitor will charge up, or if the current tends to flow in the other direction, capacitor will discharge and eventually it will reach VOCM. Okay. So there is no common mode current flowing through the load. The equation is simply I0 is VDD minus VOCM divided by R. Okay. Now, what is the largest swing you can get from this? What limits the swing? The differential pair getting into triode. So, yeah, what is the best? So, the worst case is let's take a single differential pair. The equalizer is the same thing split into multiple parts and connected in parallel, and each one receives a different input voltage. Okay. So, the worst case is when this tends to increase, the gate tends to increase, the drain tends to decrease. That's when it will drive this transistor into triode region. Okay. So, when it's fully switched and the gate, when the differential pair is fully switched, what is this voltage? The common mode voltage is what? My VDD minus I naught R by 2. This is the common mode voltage. When it's fully switched, what is this voltage going to be? Minus? When this gate is up, this gate is down, such that the differential pair is fully switched, what is the drain voltage? Minus I naught R by 4. Why I naught R by 4? Yeah, the current, I mean, there is some current flowing in this particular case, like this, right? Okay. So, for the differential picture, these two resistors appear in parallel with the drain resistors that are connected to VDD. Okay. Minus 3 times I naught R by 4. Basically, it is this value minus a further I naught R by 4. This is the common mode value and this is the signal swing. Okay. So, it also means that the other node, when this goes down, this does not reach VDD, it will reach VDD minus I naught R by 4. Okay. So, we know this VDD minus I naught R by 4. So, what is this? What is the maximum value for this voltage? No, I know, but if the drain voltage is this much, what is the maximum the gate voltage can have? Plus 1 threshold voltage, right? The drain voltage has a certain value. Now, to keep it in saturation region, this can go above the drain, but not by more than 1 threshold. Okay, so that's the maximum switching level you can have. And this should be equal to the input common mode voltage plus the input switching voltage. Okay. This will be the input differential peak to peak divided by 4. Okay. So, if the differential input peak to peak is certain amount, that means that each side goes up or down by that divided by 4. Okay. So, that essentially, I mean, there is not much more to the design of this, and when the input is okay. when this is just on the verge of, when the differential pair transistor is on the verge of triode region, you will have just the saturation voltage of the transistor. Okay. And this will be also, this should be in saturation. Okay. So let's say in the quiescent condition, what is the worst case for this transistor? When the, yeah, when the differential voltage is 0, this will be the smallest. Okay. So let's pick that smallest voltage to be some value so that it is comfortably in saturation. Now, when it switches completely, what is the voltage going to be? When it's 0 differential input, it is the smallest, and when it switches completely, what is the voltage? So anyway, this will have a certain saturation voltage when it's carrying all of I naught. So the maximum input voltage minus the threshold voltage minus that saturation voltage. Okay. This is the saturation voltage of the differential pair transistor when it's carrying the complete current. Okay. So how would you, what do you do to maximize the swing? Yeah, that's true. That is true. What is the worst case for the, what is the, Yeah, that's right. So anyway, how do you, what do you do? There are different things that you can adjust, but what do you do to the input common mode voltage to get the maximum output swing? Yeah. Yeah, so you have to, basically you have to minimize the input common mode voltage, right? That part is clear. So this is some fixed part, and this is a characteristic of the differential pair transistor. This is something that you choose, the input common mode voltage. So to maximize the swing, you have to minimize it. But when you do take it to some very low value, the tail current source goes into triode region. Okay, that is the problem.
Sir, but the limit occurs somewhere like 0.8 volts.
What is?
The input common mode, we can't go below.
Yeah.
This condition is around 0.8.
Yeah.
But given that we have source follower between the flip-flop and this driver there, we can't go beyond a few, maybe a threshold a little over the threshold for the common.
You can't go little over a threshold, meaning?
As in, the flip-flops are designed with 1.65 common.
Okay, let's just take the differential pair, right? Yeah, so you may have to change something else that is driving it, but if you just take the differential pair and optimize it, the smallest value of common mode voltage, you can drive it with this, the saturation voltage to sustain the current source, plus the VGS of the differential pair. Okay? This is VD sat of the tail plus VD sat of the diff pair when it is carrying a current I naught by 2, okay, plus VT, okay. What is the differential switching voltage of the differential pair? No, no, I mean, what is it in terms of its bias condition? Road 2? It's the overdrive when I naught is flowing. Okay. So, switching voltage is, this is the differential voltage. Okay. So, to calculate the peak to peak, you have to take twice this value. So, this is nothing but square root 2 of VD sat of the diff pair when I naught by 2 is flowing. Okay. And what did we want this value to be? Yeah. So, the peak to peak differential input voltage is 600 millivolts. So, you have to make this less than 300. Okay. So, let us say we make it just for the heck of it 280 millivolts. Okay. So, you should actually make it even less, because otherwise it won't switch completely. You would like complete switching, but then the transistors become very large, and so there is a trade-off here also. You can make this switching voltage very small, but then the transistors become very large. The previous stage has to drive a lot of current. Okay. So, I made this 280 millivolts so that this term is 200 millivolts. Okay. So, if this is the case, then the input common mode voltage must be adjusted to, I said you pick about 200 millivolts for this. Again, you can make the tail saturation voltage very small. What happens in that case? Why should I not make it as small as possible? The capacitance from the tail node, which causes current transients, that will increase. Okay. So, that is the reason to keep this at some reasonable value. You can make it, let us say 150 to 200 millivolts or something. So, in this case, I make this 200 millivolts. I make this also 200 millivolts. And what is VT? Half a volt, right? So, this is about 0.9 volt common mode. Okay. What is the maximum value of the gate voltage? The common mode is 0.9. The voltage that you apply is 300 millivolts peak, right? 1.05. Yeah, that's right. 1.05 volts. So, it's 600 millivolts divided by 4. Is that part clear? I want the switching voltage to be 600 millivolt peak to peak differential. That means each side goes up or down by 150 millivolts. Okay. So, the gate can go to a maximum of 1.05 volts. So, what is the lowest voltage the drain can go to? Huh? 180 below this. Okay. And that is 0.65 volts. Right? Oh, sorry, 0.55 volts. That's correct. 0.55 volts, and this is VDD minus 3 by 4 I naught R, and VDD is 1.8 volts. Okay. So, what is the swing that you can get at the output? What is the differential swing at the output? I naught R. That is the differential peak to peak swing. So, if we have I naught flowing here, the effective load resistance is R by 2. So, it can be either I naught R by 2 or minus I naught R by 2. Okay. So, differentially it is, peak to peak it is I naught R. So, how much is this? What? 5 by 3 volts. Yeah. Is this correct? 1.8. $1.25, right? 1.25. Okay. Yeah. So it is 5 by 3 volts. What's the differential amplitude you got? 1.5 volts. Everyone? Okay. No, actually, so this exercise is just to see what is the maximum swing that you can get given the constraints on technology. So I have myself mentioned in the assignment that when you add the source follower and everything, you have to do some redesigning, and the swing will in fact get compromised a little bit. Okay, but some of you have designed it for very low values. I think you designed it for 1 volt or 800 millivolts or something, right? Why? Yeah, so you can do a lot more than 800 millivolts. Okay, so 1.61 volts. This is if all the gate voltages are at the optimum and so on. So maybe you should be able to do something like 1.5 volts, 1.4 volts. Okay, you got 1.8. I mean, it's R roll. Huh? Which one? Yeah, that's true. I mean, this need not be 200 millivolts. Okay. Yeah, whatever it is, it doesn't have to be. The saturation voltage doesn't have to be 200 millivolts. If you pick it to be a little less, you can get even higher swing than this. But roughly speaking, like 1.7, 1.8 volts is probably the maximum you get, and you can easily do 1.5 volts. Okay. So let's pick 1.5 volts conservatively. What is the tail current we need to drive this? What is the tail current for this corresponding to this? Huh? How much? R, yeah, well, R is 50 ohms, right? So I naught R is nothing but the differential output peak to peak, and R is 50 ohms. So I naught is 30 milliamperes. So it is a larger current than what probably most of you are used to in IC design. But if you want to drive such a voltage across such a resistance, you have to have that much current. That's it. There is no arguing with the numbers, right? So that means that your transistors will be rather wide. But I mean, that's the way it is. That's all. It's just the way numbers come out. If you want to drive 1 volt into across 50 ohms, you have to have how much? 20 milliamps, right? That's the bottom line. So your so some of you, I mean, I went through the numbers, and I think most of you have numbers in the range of 30, 32 milliamperes, something like that. Some of you have very low numbers like 20 milliamps or even less. Okay. So you can do this, and then if you are, so the circuit I have drawn here is just a driver. There is no equalization. Now if you want to make an equalizer with a certain tap ratio, you can't do any better, right? The worst case is still the same. One of the inputs is high, the corresponding drain voltage is low, and that's what limits the output swing. The equalizer is not in any fundamental way different from this circuit as far as swing limits are concerned. Okay. So you simply take this, let's say, what are the coefficients? Yeah. So 0.25, 1, 0.5 and 0.25. So these are, I mean, this is minus and this is also a minus, but it's the absolute sum that we are concerned with. So we simply split it up into 4 differential pairs with the corresponding ratios. So what is it going to be? This is 15 milliamps, the cursor. This is 7.5 milliamps. So let me make it 32 milliamps just for the heck of it. So this is 16 milliamp. This is 8 milliamp, 4 milliamps, and 4 milliamps. And of course, because of the minus sign, this differential pair and this differential pair are connected in opposite sense at the output or the input, one of them. Okay. So if you do this, then you get the equalizer with these taps. So this is 4 milliamp, 16 milliamp, 8 milliamps and 4 milliamps. The inputs all have this polarity, and you apply xn plus 1 to this, xn minus 1 and xn minus 2. Okay, so that's all that is there to the design of the equalizer, and each one should have an input amplitude of 600 millivolts to switch them completely. So now you have the current, and from this you also get the W by L, right? Because we chose certain overdrive voltage. Okay, and you can also get the W by L for the tail. Now to split it into 4 parts, you split each of those things into 4 parts, right? So you reduce the current. I mean, this current is some fraction of the total current. The W by L of this is also some fraction of the total W by L. Okay. What is the width of the order of magnitude of the width that you got? 100 micron. So let's say this whole 32 milliamps, if you made a non-equalizing driver, it would go through a transistor of 320 microns by 0.18 microns. Then this would be 40 microns by 0.18. Okay. So these will be the sizes of the differential pair switches. Now for the differential pair switch, you will not use anything other than the minimum length, because there is no point. I mean, if you increase the length of the transistor, you need more voltage to switch it. You are simply adding to the input capacitance. That's all. Okay. So you always use minimum size devices for the switch. For the tail current, you can choose to use more than minimum size if you find that makes a better current source. Okay. 150 millivolt switching. So that is, yeah. Yeah, I mean, I have not actually, see this, I didn't get it out of calculation. I just picked some numbers so that I could divide it easily. So, but it will be something similar to this. It is not going to be 10 micron, it's not going to be 10,000 micron, right? Somewhere in the middle. Okay. So I think, yeah, this part is pretty simple. You just connect it up. And when you, what happens if you supply an alternating bit pattern? What is the output amplitude you will get from this? Yeah. The question is, when you feed an alternating bit pattern to this equalizer, what is the amplitude you can get? See, the amplitude we were supposed to get was in this, for these current values, 32 milliamps times 50 ohms, that is 1.6 volts, peak to peak differential. Now, X of n is an alternating sequence, okay. What is the output amplitude I am going to get? 1.6, why? So, the weights are like minus, plus, minus, plus, okay. And when those things are convolved with this type of input pattern, you get the absolute sum of the weights, okay. So, you will in fact see 1.6 volts. That's the point of that exercise, to see that you will in fact get the maximum amplitude in that. Yeah? Huh? Sizes have to be the same? No, they should not be. Yeah, I have changed the current and I have changed the, I want to essentially scale the entire differential pair. I don't want to change the input switching voltage and so on, okay. That is irrelevant, right? I mean, basically, let's say I even had ideal sources here, okay. So I have somehow I had designed a driver without equalization that gives 1.6 volts peak to peak differential and that gives 32 milliamps, okay, and it had a certain width. How would I split it up into different taps? I want each tap to have the same switching voltage, okay. So I have to scale both the current and the W by L, isn't it? Yeah, all switches should have different sizes. Did you use it or not? Did you guys use the same? How many of you use the same size? Yeah, yeah. I mean, this is already designed properly, right? Yeah. Chap rate changes? I missed what you said. Yeah. Yeah.
Then here, like if we have designed for a maximum of 1, then if we put the same digital equalizer tag, then we can change anywhere.
Yeah.
But here we have to be very specific that we can change only like some range in the first tab and some range in the second.
Yeah, yeah. I mean, the first tab can have a magnitude of 0.25 maximum.
Yeah.
But when you calculate the values of the previous segment,
Yeah.
it's 0.25 something.
Okay. I mean, you mean 0.251 or 0.2501. No, no. See, this equalizer is designed for a maximum weight of 0.25, right? That's the other. Okay, but I mean, what is the argument for using the same size for all of them?
No, you over-designed it for one of them, so you can substitute any.
No, you have severely over-designed it now, right? No, but that is a kind of wastage of resources because your tabs are not going to be that high, right? Your tabs are not going to be as high as the cursor. Not any values. I mean, your response will be like this, right? This will be the cursor, and the other tabs will be smaller than the cursor. Yeah, that's correct. So this is a correct equalizer design where the maximum weight is 0.25 for the precursor tab, 0.5 for the first post cursor tab, and 0.25 for the second post cursor tab. Okay. I mean, there is always going to be a limited range, right? You certainly cannot change it over an infinitely large range. You are going to be limited based on the number of channels that you studied or something of that sort. Yeah, but it's a severe over-design, isn't it? And finally, okay, what is the amplitude you will get in that case? The amplitude will be smaller, isn't it? Why will it be the same? I mean, so you are assuming that coefficients go anywhere when you are doing the sizing, but not anywhere when you are using the current, is it?
What they done is, if the size is the same, you design it for the cursor current. The cursor kilowatts of current.
Okay.
You take the size for that. And you put that size for all the others.
So you have basically designed it. The cursor current it will switch, that's correct. But what is the tail current in the other three differential pairs?
The tail current is for the other cases lesser than that.
Okay, let's. Yeah, so is that what you have done? You have scaled the currents but not the sizes, right? That's the bottom line. So what I am saying is that's not going to give you any advantage, right? Why did you scale the currents? Yeah, to change the coefficients. Now, why do you not want to change you already used a certain value of, you have limited yourself to a certain value by the current. Why do you not want to scale the width? Yeah, that's correct. So, whatever I have described assumes that the maximum values are this much for each coefficient. Okay? No, but can you really do that? How? Because if I do, so you have, what is the current you have for the cursor? Let's say 16 milliamps, right? Now, can I put 16 milliamps in all four of them? How? No, if you want you can put, but will the equalizer work? What happens if you put the 16 milliamps into all four of them? Huh? No, this is, okay, firstly, I don't know if I have explicitly said that the coefficients are limited to this. I think I have said that the coefficients are this, okay. So this is the kind of maximum equalization that we will do. But besides that, I am talking about this whole idea of scaling the currents but not scaling the width, okay. So your width is sufficient to handle the 16 milliamp current. Let's say you also, I don't know what you designed it for, let's assume that the cursor current is 16. So your width is sufficient to handle that. But can I put 16 milliamps into all four tabs? What will happen in that case? Huh? Yeah, so you can't really drive that much amplitude, right? I can't drive 64 milliamps times 50 ohms. I can't drive that much amplitude. So if I have to design it for an equalizer whose every coefficient can be between 0 and 1, then I have to design it for a different swing. Is that okay or no? Yeah. So, yeah. Yeah. Oh, you can. Yeah, that's okay. I mean, see. Oh, okay. I have to. So this equalizer is for one precursor and two postcursor. But I could take this and slightly redesign it to get two precursor and one postcursor if I wanted, right?
We create a pulse inverter and just change the current so we can equalize for everything. We will precursor, two precursor, and the total of that.
What is the tail current you have for the cursor?
No, sir. What I said is tail current will be 16 milliamp, 8 milliamp, 400.
Okay. Okay.
I can reduce the position of the cursor. In your case, cursor is 6 milliamp, one precursor.
Yeah, that's correct.
But in my case, I can have only 3 precursors.
Because
Whatever it is. I can equalize everything.
so you are saying that you will program the tail currents. Yeah, that's potentially that is possible. Yeah. The total current will have to be limited to 32 milliamps based on the swing limit, and you found a loophole in the argument I presented so far. Yeah, that is true. No, first of all, there is nothing wrong with subthreshold, right? Let it go into subthreshold. Huh? No, it should, right? I mean, when you are varying the current, it will affect your GM, whether it's in subthreshold or not. Okay. Oh, no. The ratio is determined not by the GM because it's not operating as a small signal amplifier, right? It's only by the total amount of current. If it fully switches, the tap value that you get is based on the total amount of current. Okay. Yeah, you can certainly make it more universal, right? Meaning you can essentially have a DAC here and you calculate the inputs and you feed it. That's essentially what is happening in that case. It's like a more, with some more degrees of freedom. A current steering DAC where I could make this 16, 1 half, 0.25 and 0.25. Okay? Huh? Yeah. Yeah. Okay. Yeah, that's correct. Yeah. But that's also, that's not an unreasonable case, right? Because you do know the channels, at least the range of channels that you're going to equalize. Isn't it? It's not some totally unknown quantity. It's not likely that you will have to adjust all coefficients to 1, ever. Okay. Yeah. Yeah, you can introduce other kinds of... which one? Yeah, if the total current is the... Well, I can also, see, this is now going beyond the scope of the assignment, but I can do it by digitally equating, I can put whatever input I want into this, right? If I feed the same thing into the second one and the third one, I can give it to 0.75. Isn't it? Same for you also, because I've said I'll feed xn plus 1, xn and so on, but I can digitally adjust them so that I get something else. Maybe this is the first tab, this is the second tab, third tab and fourth tab. So that is always possible. But there is definitely flexibility when you have digital circuitry. You will have to have more complicated arrangements so that you can feed multiple things, but that's certainly possible, isn't it? So I can feed the same digital input to these two, then I can get a maximum tap of 0.75 for that particular input. Okay. So that's possible, and you can do it also by maybe having a facility to have very large coefficients for each of them, but not actually going to that unless you need it. Okay.
But there is any lower limit on the tablet which we can actually write from this.
Yeah, I mean, if you have tap values like 0.01, you will have a really small differential pair here, and it could be that you will have parasitic capacitances also. So, if the current contributed by parasitic capacitances and so on is comparable to 0.01 of the main tap, that is when the tap is really not doing anything. Okay. So, there is a limit in that sense, a practical limit. Okay. So, yeah, it is true. If you have a large enough width, certainly you can accommodate larger currents. But in this case, what I was pointing out was that if let's assume that you do have a limit on the tap coefficient of 0.25, then you scale both the width and the current. Okay. But yeah, there is you can have a flexible architecture, more flexible architecture where you can change your interpretation of which is the cursor and which is not the cursor and so on. Huh? Oh, I didn't. You have not lost any credit for it. Don't worry about it. Anyway, I think most of this reasoning is after the fact, right? If you didn't think of all this before doing the assignment. Huh? Is it? Okay. That's better. So, anyway, to scale some circuit so that all the voltages remain the same, the switching voltages and the output and so on, you have to scale both the current and the width. Okay. So, if you scale all the current by a factor of n and scale all the widths by a factor of n, the operation of the circuit remains the same, just the impedance level goes up by a factor of n. Okay. So, even in this case, in this particular case, once you pick a certain width, if you are operating, if this coefficient happens to be 0, you are operating with a different current density. That is true. But if you do know that the maximum value of certain coefficient is something, you can optimize the design a little better. So, the only disadvantage of having, let's say, equal width for all of this is your output parasitic capacitance will increase. Okay. Huh? Yeah, that's right. I mean, you have a larger differential pair, so you have to drive it with a larger one. So, if you do know the range, it's best to optimize it. If you don't and you have to cover an even wider range, yeah, then you leave it more flexible. Okay. And generally, obviously, there is a trade-off between how optimal you make it and how general you make it, right? So, if you make a very general solution, it's not going to be the most optimal. If you make a very optimal solution, it's probably going to be very specific to some case. Okay. So, the next thing is to design the source follower, because the flip-flop gives a voltage that is maximum VDD and minimum of VDD minus 0.3 or something of that sort. Okay. And you can translate those levels into the desired levels using a source follower. Okay. Now, because you don't have so much freedom over the design of the source follower. The source follower should be strong enough to drive the input capacitances, but it should also have the right voltage. Now, this is not really two independent things, right? So, once you fix the source follower size and current so that it can drive it properly, the amount of level shift you get from the source follower is also fixed. So, you don't have so much trade-off. That's why I said that you may have to compromise a little bit and also maybe change the flip-flop somewhat. Okay. So, if you make a very small source follower with a small current, what happens? It won't be able to drive. Basically, the output time constant, essentially the output impedance looking in here is of the order of GM, the output conductance, and you have a certain capacitance here. So, GM by C has to be large enough so that you get a nice pulse at the input of the differential pair. If that's not the case, then you will not have a strong enough drive. Okay. So, that's just about it. I mean, that you can adjust by just by like iterating over some designs. Okay. Now, one thing is, if you do in fact scale the differential pairs, the capacitances are all different, then you should also scale the source followers so that they have the same delay and the same behavior. Okay. So, you normally, whenever you have a buffer like this, so let's say this is 1 and this is half. You should scale this also, so that then the delay through this will be the same as the delay through this. They behave identically. If you have 0.5 and 1, then the signals through this will be of slightly different shape than the signals through this. Okay.
As long as it is faster than the.
No, there is a question of linearity also, right? You can express the whole thing as a linear time invariant system only if they are all scaled pulses that are adding together. Okay. Now you can't make it exactly, because at some point when you electronically change the coefficient, you can't scale the current densities. But still, you try to make it as you try to match the different paths as well as possible. Okay. I mean, this is a general rule that you, of course, the buffer size should be proportional to what it is driving. Again, if you have, this is going to be only 0.5 and you use the same size and current as here, it's a waste. Okay. It's like, it's one more thing that you do to further optimize your design and reduce the power consumption. Okay. So, and flip-flops, did you have to increase the size of the flip-flop? Scale it up, right? Because I think this width is very large, so even the source follower has a large enough width that whatever you designed in the first case for 10 femtofarad load, I think it was 10 femtofarad load, right? What was the, I think you had designed it for driving another flip-flop. So that was not, that's probably not going to be good enough, but you can scale everything. Again, the scaling principle is the same. The current goes up by a certain factor alpha, width goes up by a factor alpha, length doesn't change, okay, and resistance goes down by a factor alpha. Okay. So this will ensure exact scaling. This is like taking a slice of the original circuit or taking multiple circuits and putting them in parallel. Okay. Is this clear, the scaling idea? So once you do all of that, I think you should get the result to be more or less correct. The swing will be somewhat compromised because you can't level shift exactly and you won't get the same swing and some things won't switch completely, etc., etc. But some of you have got weird diagrams, you have to just go back and see why that's the case. Okay. Now when so finally what I had mentioned was that you drive the filter with this. What I meant is we don't have the channel model in this case, right? We have the equalizer and there is the source side termination, and normally there is a transmission line and the load side termination. But now there is no model of the transmission line. So we just short the source and the load. So to model the effect of the channel, what I said was you take this to an ideal filter of that transfer function. Okay, and find the output. I mean, this is not loading the circuit in any way. This is a circuit with infinite input impedance. So it's basically whatever it's to model what happens when the output waveform of the transmitter goes through an 8th order filter of this sort. Okay, and it should be able to equalize it by adjusting the taps. What will the I diagram look like at this point if all the coefficients are the maximum values? So what is how many levels will this have? I mean 16 if you include both positive and negative, but some of them are I think common because 0.5 minus 0.25 is the same as 0 plus 0.25. Okay. So you will, the bottom line is you should see an I diagram like this. So this will be one cycle of the I diagram. But this is where I don't know what it is, some mistake some people have made where the I diagram has just a single trace with some overlap. It's not clear how you got this, but there must be some mistake in the simulation. I can't debug it just by looking at the plot on the paper, but because you have coefficients, you drive it with an ideal input, you should have multiple levels, okay? And the number of levels depends on the number of, basically in this case it's 2 to the 4, except that some values are the same as some other values, okay? So this is what you should get, and then if you drive a filter through this, you should see a nice equalized I diagram, okay? When let's say the bandwidth of this is 0.67, if you don't have any equalization, you will have an I diagram at 10% opening. If you do have equalization, it should open up. Did you see that? So that's, I mean, it does work. So that's the whole idea. So I don't know, did you guys have any difficulty in simulating the last part with the filter? Okay, but there were some mistakes. You just see what they are. Okay. Sure. Any questions on this? Oh, let's just quickly finish off the PAM4 transmitter also. This is really very simple. Okay. So to get 2 bits per symbol, you use a deserializer. Okay. So you get, if this is at Fs, this will be at Fs by 2, and there will be 2 bits. And let's say 0, 0, 0, 1, 1, 0, 1, 1, these correspond to minus 1, minus 1/3, plus 1/3, plus 1. How do you make a transmitter that gives you these 4 values? So we just need 2 differential pairs, right? One with a weight of 1/3 and one with a weight of 2/3. That's the optimal realization. The maximum is 1. Okay. So let's say this is 1/3 and this is 2/3, or basically this is 1 and 2. Okay. Then you arrange it so that when you want this, both of them are on, but with reverse polarity. When you want this, both of them are on, but with the positive polarity. When you want this, only this is on with negative polarity, and when you want this, only this is on with positive polarity. So you can arrange some, from these 2 bits, the control of this goes through some digital logic, okay, to get that one. So again, this is a simple thing, but did everyone do something like this? I think some of you didn't have a deserializer in the schematic. Okay, you need to somehow go from having Fs to Fs by 2 and then do this weighting. And I think someone had this scheme using a linear GM. Usually that's not a preferred thing because you have 4 digital levels. You just use the differential pairs in a fully switched mode. You don't use linear transconductors in this case. Okay, although you can, I mean, if you want 1 and 1/3 and so on, you can generate an input voltage and make that output proportional to this or something like that. But it's not a preferable way of doing it. You just use it, you drive the differential pairs with the digital input so that they switch completely. Is this clear? The solution to PAM4 transmitter. So essentially the structure looks more or less like the equalizer. And if you want to equalize PAM4 data, you will have more differential pairs. Okay. Any questions on any of this? Okay, sounds good.